Hi, I'm Dr. Will Weber from Whatcom Community College, and this is What the H. It is my take on what to do now that I've watched students for 25 to 30 years trying to deal with the definition of derivative. Most of the textbooks that I've used over this period of time have given two definitions of derivative. They give first the definition of a derivative at a particular point. So they say, given a function f of x, we define the derivative of f of x at x equals a as f prime of a equals the limit as x goes to a of f of x minus f of a all over x minus a. And then they go on to give a definition of the derivative as a function. And so given a function f of x, we define the derivative of f of x as f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, some of the books for the second definition use a delta x instead of an h, and that's fine. I'm using an h here because what the delta x just doesn't have the ring of what the h. So, now, I'm often asked by students, even though it seems obvious to me, the question is, which one should I use? Well, let's do an example and see which one might be easier to use. So here's my example. It's given the function f of x equals x squared. Let's find the derivative of this at x equals 3. So this fits in the case where you could use either one. So here we go. F prime of 3 is, by the definition, the limit as x goes to 3 of f of x minus f of 3 all over x minus 3. Now let's apply our function, or this definition to that function. So that's the limit as x goes to 3 of x squared minus 3 squared over x minus 3. Now, you know, students in their algebra, some of them would erroneously cancel an x out here and then cancel the negative 3 with a negative 9 to get a plus 3, and they'd end up with an x plus 3. But we know better than that. That's not the way you do this problem, because you can't just cancel like that. You've got to factor first. So we factor that numerator, x plus 3, x minus 3, and then sure enough, the x minus 3's cancel out, leaving us with an x plus 3. Apparently there's a bit of error correction in this method. And then, of course, now that we've canceled out the 0 over 0, you can plug in the x equals 3 to get 6. So the slope at x equals 3 is 6. Now let's look at using the other definition. So here is method 2. I'm going to use the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. So I'm plugging the 3 in for x right from the start here, and I get this. Now, at this stage is where it really becomes tricky, right? What do your students typically do with the plus h? Well, I would say typically they do it right. But there's always a bunch that don't know what this function notation means. And the plus h gets on the outside, or even if they do get it on the inside, they're going to say 3 plus h squared is 3 squared plus h squared. Anyway, we've got to square that binomial. 9 plus 6h plus h squared minus 9 all over h. The 9's go away, the h can be factored out, and there's the 0 over 0 problem. And you've got a 6 plus h as h goes to 0 is just 6. Now, I want to do this one more way because there is another way it could be done using that second definition. So with the third method, I'm using the second definition, but I'm not plugging x equals 3 in to start with. I'm going to just find the derivative of x squared and then plug in the x equals 3. Okay. Now, f of x plus h minus f of x all over h, the limit as h goes to 0. That's the derivative of f. This function, when you plug the x plus h in, you get x plus h squared. Again, this is the tricky part. Do they get the plus h inside those parentheses, or are they outside? Or are they halfway in the middle sometimes? Who knows? So anyway, square that out. The x squareds go away, then there's an h on the top that can be factored out, and the h over h cancels, leaving 2x plus h as h goes to 0, which is just 2x. So now, with x equal to 3, you plug it in and get your answer of 6. So from the point of view of trying to find the derivative at a particular point, the definition for finding the derivative at a particular point is really the way to go. Right? And this is what I would tell the students. For years I've been saying, if you just need it at one point, use the first one. If you need it at a number of points, if you need the derivative at a number of points, then use the second definition. Or if you don't know where you need the derivative, then use the second definition. I've even told students that the first one only tells you the slope at x equals a. It doesn't tell you the slope anywhere else. But in the back of my mind, I'm saying, am I lying to my students? I don't like lying to my students. Because I could just leave the a in there, not plug a number in for it, and solve it as a function of a, and then plug in a afterwards. And personally, I like this way a lot better. And my thought is maybe I could do that and just eliminate the h's altogether. So here's what we're going to do. I'm going to start all over again and give two definitions. One for the definition of the derivative at a point, and another is the derivative at any point as a function of x here. So given a function f of x, define the derivative at x equals a as f prime of a equals the limit as x goes to a of f of x minus f of a all over x minus a. This is exactly the same as it was before. Now I want to say, for the general derivative, given a function f of x, we define the derivative of f of x as f prime of x, and it is the limit as a goes to x of f of x minus f of a over x minus a. The picture is over here. This is typically a picture that we would draw. You've got this point a, and you're going to, for this first one here, you're taking the limit as x goes to a, and we always typically draw it this way with x being bigger than a, although when you say limit, it's maybe bigger, maybe smaller, but it goes to a from either direction. And you can see the secant line, you're calculating the slope of that secant line, and as x approaches a, this point moves along the curve down to there, and the secant line becomes a tangent line, and you end up with the slope of the tangent line. Yay! Well, rather than letting x go to a, down here I'm saying, let a go to x. Won't I end up with the slope of the tangent line at x? It seems like I should, so that's what I'm going to do. Let's go through a bunch of examples. These are ones you would probably do in an introductory calculus class when you're first learning derivatives using the definition. I'm just going to run through a bunch of them that we would do. So here we go. X squared. We've actually seen this one already, but we did it with the x plus h version of the definition. So here's what it looks like with this new definition. F prime of x would be the limit as a goes to x of f of x minus f of a, all divided by x minus a. This is just the definition. Now let's apply that to our function. F of x is x squared, f of a is a squared. Again, you could do that really weird canceling stuff, but let's not do that. Let's factor and cancel. X squared plus a squared factors into x minus a times x plus a, and the x minus a is canceled out. That's the 0 over 0, and then you've got the a going to x. So this a would then be turned into an x, and you got x plus x, which is 2x. So the derivative of x squared, I'm claiming, is 2x. Is that any easier or harder than it was to do with the x plus h? It's maybe similar. A little different algebra because I'm factoring rather than multiplying out. Let's try the next one. How about x cubed? The derivative is the limit as a goes to x of f of x minus f of a all over x minus a. Of course, that's just the definition. Let us now apply our function to that, or that to our function, one way or the other. F of x is x cubed. F of a is a cubed. And here's where, they got to do a little bit of algebra that maybe they're not used to. But then again, if we were doing the x plus h version of it, you'd have that x plus h cubed that they now have to cube that polynomial. One way or the other, you got to do some algebra. One of the things, though, that I like to point out to them is that you're not, I need to factor this, but I'm not factoring in the blind, right? I'm not factoring, like saying, hey, 5,127, factor it. I'm saying, hey, 5,127, 3 is a factor, find the other, right? It's a little easier to do because you've got some information, right? When we're doing these, I keep saying there's a 0 over 0 problem, although I haven't really talked about a 0 over 0 problem yet. When you're doing limits, really the first thing you should do is plug it in. A is going to X. So turn all your A's into X's and see what happens. If you get a number, then you're probably dealing with a continuous function, and that's the limit. But if you get a 0 divided by 0, that means something's amiss. Something may be amiss, but something may be okay, right? You got to do more work. Well, at the same time, when you plug something into a polynomial and you get a 0 out, that tells you something about the polynomial, right? If you plug in x equals 2 into a polynomial and you get 0 as an output, then x minus 2 is a factor, right? So I wouldn't be looking to factor this thing top and bottom if I hadn't gotten a 0 over 0 when I tried to plug the a equals x in. This is 0 over 0. And since that is the case, then x minus a has got to be a factor of the top. So there it is, and then you could do long division, whatever, to get that other one. And, or maybe you know how to factor cubics from your algebra classes. Either way, the x minus a's cancel out, and now I can say let the a go to x, so all of those a's are going to turn into x's, x squared plus x squared plus x squared, which is 3x squared. Awesome. Is that any easier or harder than doing it with the plus h? I think it's comparable in the amount of algebra you have to do, but it eliminates the pesky plus h, which might just end up outside of the parentheses and cause problems. Here's another one, x to the n. Now I have to admit that this is one that I really have a good time with doing it with the plus h's, because we get to do Pascal's triangle, and how do you do x plus h to the n? How do you multiply it out? So I'm giving up that in order to do this way, but this has its own charm. So here we go. The derivative would be the limit as a goes to x of f of x minus f of a over x minus a. That's, of course, just the definition. I now want to apply that to my function. F of x is x to the n, f of a is a to the n. If I plug in the a going to x, so plug in an x here for a, then I get a 0 over 0. It means I got to do more work. Factor this thing. Again, like the last one, I'm not factoring in the blind. I've got one of the factors already because I plugged in an x for a. I know that x minus a is a factor, right? Because I got a 0 out of it. So x minus a is a factor. You can do polynomial long division or something else to get that thing. One of the things I like to say here as we're doing something like this is that I will often remind students that calculus is the best review of algebra they will ever have. We use every scrap of algebra that they'd ever learned, and maybe some that they haven't, right? And factoring x to the n minus a to the n is probably a little bit of algebra that they never ran across. But it always factors, no matter what n is, as well, as long as it's an integer, positive integer. It will factor. And with it factored like that, you've got the x minus a's canceling out, leaving this. Now take the limit as a goes to x. So all those a's turn into x's, looking like this, which, notice this is an x to the n minus 1, this is an x to the n minus 1, this is an x to the n minus 1, and so on. Every single one of those terms is x to the n minus 1. You then need to just figure out how many of them there are. Well, if I look at the terms that came from the a's, there's no a's here, there's 1 a there, there's 2 a's there, all the way up to n minus 1 a's. So there is a term for each of the integers 0, 1, 2, up to n minus 1, which is n different things, and so there are n terms here, and we have n times x to the n minus 1 as the derivative of x to the n. Perhaps that coincides with what you've learned before. Right? When we use the plus h version of this definition, that n comes from essentially the second entry in Pascal's triangle on whatever row you're looking at. It's a 1, n, and then a bunch of other stuff. And I don't care what that other stuff is when I'm doing this derivation because that's all going to turn into a 0. But here, the n shows up because you're adding n of the same things together. Next example. The square root. Yes, let's do the square root. So the derivative of the square root, definition, the limit as a goes to x, f of x minus f of a over x minus a. The limit, sorry, that's just the definition. We will to apply that now to this function. So this is the square root of x, f of a is the square root of a. Again, what would have happened with the plus h? Would the plus h have gotten underneath that square root? Don't know. Even if it was under the square root, would it then have been written as the square root of x plus the square root of h? Which is a very common thing. Yes. So let's just leave that h out of there. We don't have to worry about it. Typically, what a textbook would do on this problem is that they would rationalize the numerator. They'd multiply top and bottom by the conjugate of this thing, so square root of x plus the square root of a, which is perfectly okay to do, but that's not the way I'm going to do it, because I don't like doing it that way. I remember learning how to rationalize denominators, because they didn't teach you to rationalize numerators when you were in elementary school or whatever. If you had something like 6 over the square root of 2, right, how would you rationalize that denominator? Multiply top and bottom by radical 2, and then you'd get 6 radical 2 over 2, and then you could cancel the 6 and the 3 to get 3 radical 2. And it always bugged me. It's like, why am I taking 2 steps to do this? Why am I making both numerator and denominator bigger only to be able to make them smaller? What if I could just see how to make them smaller, right? It's like, sure, take 3/6 and write it as a simplified fraction. You say, oh, 3/6. Well, that would be the same as 6/12, which would be the same as a half, right? It's like, there's that extra step in there. It's always bugged me. So rather than multiplying it only then to cancel something out, let me just factor the denominator here, right? Like I would have done with 6 over radical 2. I would have written 6 as 3 times radical 2 times radical 2, and the radical 2's would cancel out, one of them anyway, leaving a 3 radical 2. So here, factor this in the denominator, square root of x minus the square root of a times the square root of x plus the square root of a. Those things cancel out, leaving just a 1 on the top and a radical x plus radical a on the bottom. Now I can plug in the a going to x, so that a turns into an x, and it looks like this. And it turns out that the derivative of the square root function is 1 over 2 times the derivative of the square root of x. All right, let's move on to the next example. All right, in this example, I'm looking at f of x is 1 over x. Again, standard one that I typically do with the x plus h definition. You've got to get the plus h in the denominator, right? Is it going to end up there? Sometimes. Anyway, here we go. Take the limit as a goes to x, f of x minus f of a over x minus a. That is, of course, just the definition. I need to apply that to my function here. And so I get the limit as a goes to x of 1 over x minus 1 over a, all over x minus a. And now I've got to simplify this fraction, right? It's a 3-layer fraction, get it down to 2 layers. There's various ways that people do this. I like to just find my denominators. There's an x, there's an a, and multiply top and bottom by all those denominators. So multiply by ax. And when you distribute that into the top, you get the x's cancel out here and the a's cancel out there. So I end up just with an a minus x. And on the bottom, I'm not going to multiply it out because I know what I'm trying to do. I'm trying to cancel out the 0 over 0 problem, which the x minus a is the 0 on the bottom here. That's what I'm trying to cancel out. So I'll leave it factored so I can cancel it. And sure enough, that when I get that a minus x on the top, I can factor a minus 1 out of it. And then I've got an x minus a top and bottom, cancels out, leaving minus 1 over ax. A is going to x, so that a turns into an x, and I've got minus 1 over x squared, which I think you will agree is the derivative of 1 over x. 2 more examples I want to do here. Yes, an exponential function. B to the x. Here we go. The derivative. The definition here, right? F of x minus f of a over x minus a. Take the limit as a goes to x. Apply that to this function. F of x is b to the x. F of a is b to the a. Now, before I go on, I want to make a note that f prime of 0 here, if I plug a 0 in for x, there, there, it looks like this. And b to the 0, of course, is 1, and 0 is 0, and so this looks like this. The derivative of this exponential function at 0 is the limit as a goes to 0 of 1 minus b to the a over negative a. I'm going to use that a little bit later, but I want to just note it right here. Okay, now coming back to this derivation, I'm going to factor b to the x out of the numerator there, so we're just left with a 1 there, and this is left with a b to the a minus x. Now I'm going to slip that b to the x out in front, and this seems weird because generally you can't take functions out. You can only take constant multipliers out of the limit, but I claim this is a constant multiplier because the variable here is a, right? Remember that picture that I had? I had a and I had x, and I was letting a go to x, not the other way around. So x is staying constant, the a is the thing that's sliding, okay? So this is a constant b to the x that can come out of that limit because a is the variable. And now I want to just rewrite this limit by doing a substitution here. I'm going to let theta equal a minus x. So notice as a is going to x, a minus x will be going to 0. So this is the limit as theta is going to 0. The denominator is negative theta, and the a minus x and the exponent there is just theta. So this turns into a limit as theta goes to 0 of 1 minus b to the theta over negative theta, which is precisely that one up there with thetas instead of a's. And so this is the slope of this function at 0. So the derivative of an exponential function, b to the x, is b to the x times the slope of that function at 0. And thinking about the way exponential functions look, right? They're really flat on the negative side, and then they go up quickly. They all pass through 0, 1, and they all pass through with slightly different slopes. And depending on which one you choose, that's the multiplier you need. Now, there is one very special one, perhaps you saw this coming, where the slope as it passes through 0 is equal to 1. And so the derivative of that one is just the same as itself. We call that very special value of b e. So the derivative of e to the x is e to the x. One last example here. The sine. We've done polynomials, we've done exponentials, let's do a trig function. So the sine of x is the derivative of the sine of x. Well, the definition says as the limit as x goes, no, not as x goes, as a goes to x of f of x minus f of a over x minus a. That's, of course, just the definition. Now we need to apply that to this function. F of x is sine x, f of a is sine a. Now, you think about what we would have done with the x plus h version. You'd have had a sine of x plus h here, which then the next thing would do would probably say, even if they got the h on the inside, they say, oh, well, that's the sine of x plus the sine of h. It's like, no! There's, of course, trig identities, and we would have used a sine of a sum to break that up. And then there's some shenanigans you have to do with that. But instead, what I'm going to do is I'm going to use a different identity. I'm going to use a sum to product formula. And I really like the idea of using a sum to product formula, because what was it we were doing with all those polynomial examples? We had a sum, we had a polynomial, and we factored it. And what is factoring if it's not turning a sum into a product? Right? So I'm taking the sum or difference of two signs and turning into a product of sines and cosines. Now, this would probably be an opportunity for me to do an aside if I was teaching this in a class and say, let's do a quick review of where this trig identity comes from, because generally they haven't had a lot of opportunity to use their trig yet. They've just had it the last quarter, and now they're in a Calc 1 class. So it's good to refresh them on that, or show them maybe for the first time. They haven't seen that sum to product formula. Anyway, I like doing that. In fact, I actually like teaching lower level mathematics to higher level students because they're actually ready to learn it. So anyway, so here it is. The sine of x minus the sine of a is 2 times the cosine of x plus a over 2 times the sine of x minus a over 2 all over x minus a. I'm going to split this up into two limits because I can write it, the function here as a product, and so the limit of a product is the product of the limits, provided both of them exist. And this one certainly does exist. The cosine as x goes to a, as we'll see down below here. And then everything else is here. Now notice I've got the times 2 here, and I'm writing it as a divided by 2 in the denominator. So rather than multiplying by 2, I'm dividing by a half. But I'm doing that so that this denominator looks just like what's in the sign. And then I'm going to do a substitution where theta is that stuff, x minus a over 2. And as a is going to x minus a over 2 is going to 0. So this limit turns into the limit as theta goes to 0 of sine theta over theta. And in the previous section of a calculus course, where we just introduced limits, I would have gone over this limit here, and they would know that the limit is equal to 1. Of course, this first one here, the cosine, as a goes to x, you got x plus x over 2. Well, x plus x is 2x divided by 2 is just x. So this is the cosine of x times 1. And we find that the derivative of the sine x is the cosine of x. You could also use this to prove the product rule and the quotient rule. I just find that by not using the h, I can do all of this introductory derivative stuff using a definition that's a little more user-friendly algebraically for my students.